Our primary presenter here is David Wall. He graduated from Auburn University in 2009 with a Bachelor's of Aerospace Engineering, in 2010 with a Bachelor's of Mechanical Engineering, and completed his Master's of Science in Aerospace in 2012. He began his career as a thermal analyst for Boeing, working the SLS core stage, focusing on the systems tunnel. He transited to McLaurin Aerospace in 2015, where he was contracted to Teledyne Brown to perform thermal analysis on the launch vehicle stage adapter. Today, he remains with McLaurin Aerospace under the Jacobs ESSCA contract as the lead thermal analyst. We also have a secondary presenter. Her name is Deborah Hernandez of the Jacobs Technology ESSCA group. Huntsville has supported MSFC thermal analysis since 1990. She has been supporting microgravity experiments for approximately 18 years, as well as thermal system design for ISS, Ares, and SLS. Currently, she is working supporting Marshall's Space System Thermal and Mechanical Analysis Branch, ES22. Their presentation is titled A Thermal Review of the Sample Cartridge Assembly, Gravitational Effect of Distortion in Sintering Experiment Flight Processing. Ready when you are, David.
Okay. Good afternoon or good morning, depending on where you are. Again, my name is David Wall, and today we're going to be doing a little program review for the SACA for the PI. This particular PI is the GEDS, which is the gravitational effect of distortion and sintering. So mainly we're going to be talking about what a SACA is today. What a SACA is, this first PI that we ran, which is the GEDS PI. What the GEDS flight cartridge looked like. We'll go over a flight processing profile for this cartridge, and we'll also show a comparison of TC to sample transient predictions, and then we'll discuss how the TC error impacted on predicted sample response. And then we'll go on to some forward work, lessons learned, and then we'll open it up to questions. So first, what is SACA? And we'll talk a little bit about what is a SACA, where it is processed, and some information about it. The SACA is processed in the low gradient furnace, which is the LGF, and in the Material Science Laboratory, the MSL. The Material Science Laboratory has two different furnace inserts, the LGF, the low gradient furnace, and a solidification and quench furnace, the SQF. The MSL is an ESA payload, the European Space Agency. It's a payload that's on the International Space Station right now. It is operated by the Microgravity User Support Center, MUSC, in Cologne, Germany. MSL is housed in NASA's Material Science Resource Rack, or the MSRR, in the U.S. lab module on ISS. And in the lower left-hand corner here, this is a thermal desktop model representation of what a SACA is. And I'll go over some more details about the actual cartridge here in a minute. And this is a CAD drawing of the SACA cartridge in the lower right. So the SACA cartridge is processed, again, it's in the Material Science Resource Rack in the Material Science Laboratory. And outlined here in green is the Material Science Resource Rack. This, of course, is not in the space station. It is when it was still on the ground here at Marshall. And then the one side of it has MSL, which is the Material Science Resource Rack lab. And then the core facility is right here, and inside this core facility is the LGF or SQF. And in our case, we're using the LGF, the low gradient furnace. Right here is a photo of what the LGF looks like, what the insert looks like. And in the lower right-hand corner here, this is a cross-sectional schematic view of the LGF, and it shows the 7 heater zones. So we have 3 heater zones in the cold zone, or what is defined as the cold zone, a adiabatic zone in the middle, and then 4 heaters in the hot zone with a booster heater in the middle. And this whole furnace can actually translate as well. But for this experiment, the furnace does not translate. It's stationary. So what is the SACA? The SACA stands for Sample Cartridge Assembly. It consists of a plasma sprayed molybdenum cartridge with an aluminum liner brazed to a stainless steel head. So the plasma sprayed tube is this long, about 18-inch long tube, and it's brazed into a stainless steel flange right here. And the cartridge holds flight principal investigators, or PIs, science, and provides a level of containment for safety. So down here we have our cross section of our furnace again, where we have our cold zones and our hot zones. And so all the PIs would like something in the hot zone with a nice isothermal, typically an isothermal gradient, and this particular PI does want an isothermal gradient. So we have his science, which is located here down in the hot zone of the furnace. And it's the stainless steel SACA head contains a pressure transducer, a temperature limiting resistor, and mounting locations for all the thermocouple transitions. So all the thermocouples are mounted to a band up here with essentially a stainless steel zip tie, and they all extend down into our hot zone to whatever length we desire. Again, there's an absolute pressure transducer in the head as well, so we can monitor the pressure inside the cartridge. So what is the GEDS experiment? Well, first it's an experiment by Dr. Rand German. He is the PI based out of San Diego State University. The GEDS experiment focuses on determining the underlying morphology that governs density, size, shape, and properties for liquid phase centered bodies over a broad range of composition in Earth gravity and microgravity conditions. Samples are processed by holding the ampule at an isothermal condition for a prescribed period of time to obtain a snapshot of liquid phase centering for various exposed times. So, this is the science behind it. Again, we're thermal analysts. We mainly have been focusing on the thermal side of it, but wanted to put this in here to tell you a little bit about the background of the science of GEDS. And here in these images here, these are his samples. He had 7 samples in each cartridge, labeled 1 through 7. And you can see he has outlines around each one of these samples. And these are actually samples from the GEDS C5 cartridge that we processed last November, December, and we have actually gotten these cartridge samples back. And the outline around the sample is how big the sample was originally. So it's just something to note that the sample shrank as after processing. So each cartridge is made up of 7 samples contained in crucibles, and each sample is primarily tungsten with varying percentages of nickel, copper, and manganese, and that was all determined by the PI. So each cartridge has 7 samples, but we also have 7 SACAs for the GEDS experiment. And we refer to them as GEDS C0, 1, 2 to 6. And the science goal is isothermality at temperature over exposed time. So he would like all the samples to be at a particular temperature. So cartridge 1 wants to be at one temperature, at a temperature for a duration. Cartridge 2 at the same temperature for a different duration, and so on and so forth. So again, you can see we have a CAD model, a thermal model, and what we wanted to note here was that our thermocouples, we have redundant thermocouples at the 2nd sample and at the 7th sample. And this is so that we can determine what kind of gradient we have through our samples. We also wanted to note that the farther into the hot zone, so sample 7, is a more higher priority sample for the PI compared to sample 1. So this chart shows each one of the samples for each cartridge, how long we were going to have a temperature hold at the PI's desired temperature, and how long each one of the samples would be above the PI's desired temperature. So the PI was asking us to have the samples at or above 1205 degrees Celsius. So this top chart shows, based off of our predictions, how long each sample would be above 1205 degrees if we held the furnace at our hold set point, how long it would be held above it. So you can see each one of the cartridges, their hold times. You'll see sample 1, it was not really predicted to go above 1205, but we'll point that out in a little bit. If we go down to the next one, it shows that these are the maximum temperatures that we expected during all of these. And so you can see sample 1 was really, really close to 1,205 degrees Celsius. And when we did all this, the model did not simulate sintering. It was just assumed a homogeneous mixture for each one of the samples. On the LGF flight calibration cartridge showed the LGF heater set point thermocouples had drifted. So prior to running GEDS, ESA ran a calibration cartridge, and this showed that when they were holding at steady state at 1,000 degrees Celsius, there was an actual 7-degree difference between their calibration cartridge and the furnace. So therefore, they had to set the furnace to 1,007 degrees Celsius, such that the cartridge would read 1,000 degrees. And then at 1,200 degrees, they were 10 degrees off. So that caused us to increase some of our temperatures for the actual GEDS processing. There are 7 heaters heated from ambient to 1050 at 5 degrees Celsius per minute for the GEDS processing, and then we allow it to steady state. And that's when the thermal group comes in to monitor what the furnace is doing and to make sure that the GEDS science was correct. And when we did our assessment, it was similar to what ESA's calibration cartridge read, and it was reading low. So we decided to adjust the temperatures at that set point up by 13 degrees Celsius, because we extrapolated out to our processing temperature, which should have been 1,210 degrees, but we had to take it out to where we would believe that the furnace set point would have to be 1,223 degrees Celsius, and we wanted to maintain a 160-degree final ramp up. And I'll talk a little bit more about that ramp up here in a minute. And then once we ramp up to the 1,210 degrees Celsius, the temperature is held constant until an appropriate processing window becomes available within about 30 hours. And then this also allows for a low initial vacuum pressure inside the chamber, and I'll talk about more about that in the next slide. And then we also were looking for a processing window during crew sleep so that there was no G loads going on in the space station at the time. And then we were also looking for a 30 to 45-minute window of very good data coverage so that we could send any commands from the ground to change any furnace settings if we needed. So this is this plot here shows a typical hot zone temperature and pressure profile. But it's typical, but this is actual data from the GEDS C5 flight run. During the final heat up, the hot zone heaters 4 through 7 are heated to 1210 Celsius at 10 C a minute. And that's what this ramp is here. And you can see it does overshoot a little bit. And then we go into our steady state hold for the PI's desired duration, and then we cool down. We also watch the pressure profile, which is right here during that time. So for GEDS, it's critical that we do not have an unexpected hold during this final heat up. So irreversible damage can be done to the PI's science during these holds, because the damage being caused from these temperature holds where the PI is not requesting them. And so if you remember, the PI is looking for temperature holds between 30 and 90 minutes. He assigns them, which has so each one of these, if we have a pressure hold, it'll add time at an undesired temperature for his results. So the furnace has an internal pressure limit of 10 to the minus 3 millibar, but we had a waiver to raise this up to 7 times 10 to the minus 3 millibar. And if the furnace reaches these pressure limits, what it does is it stops heating during that ramp, and it will go into a temperature hold, and it will hold there until the pressure, until the vacuum system will bring the pressure back down to 3 times 10 to the minus 3 millibar. And these pressure holds can last anywhere from 30 to 60 minutes. So they're, so that's unwanted time that the PI does not want. So these vacuum holds are for the limits that are actually on the furnace and the vacuum system itself. If the pressure in the furnace gets too high, it can do damage to those systems. Again, we get a temperature and we hold, we process for that time, and then we control it cooling down until we hit the 800 degrees Celsius, and then it's allowed to free fall from there. So a thermal mass model for the SACA was also constructed, and this was to get an internal response of the actual samples. And since these samples are rather heavy, since they're made out of tungsten, they showed a lagging response compared to the very lightweight platinum thermocouples and to the furnace thermocouples. So the thermal mass model simulates the furnace response with transient boundary conditions. And also due to the LGF heater setting drift, the SACA TC data, instead of actual heater data set points, was used to control this. The thermal mass model was used and then to predict the sample response and the amount. Again, none of our thermal mass models simulate sintering. They'll assume that it's essentially just pure tungsten. And then we evaluated some TC error based off of that. So slide 12, it shows the lag in sample temperature compared to the furnace and the SACA TCs. This data was actually extracted from the thermal mass model. So you can see this outside curve is the furnace TCs, and all these inner curves are from the samples at different, depending on which different sample it is. So this lower curve is the sample 1, the one closest to the cold end. And as we go out farther, it's closer to sample 7. I believe this gray line here is sample 7. Yeah, the gray line is sample 7, and the dash line is, the gray dash line is the crucible for sample 7. So you can see it does lag the furnace by a good bit. So the TC uncertainty translates into uncertainty in sample processing duration at isothermal conditions. This is an area of interest which the PI examines the samples and the calculated effective work of sintering. The thermocouples from here, from all the GEDS samples, all the GEDS flight cartridges except for Z0 and C3 were compared. C0 and C3 had slightly different heater set points, and that did not allow for an apples to apples comparison. The plots below here show the steady state readings of the thermocouples when the LGF was set to 1063 and 1223. And remember, there was approximately a 10-degree offset between the furnace and the SACA TCs. You can see that we were looking, we had a furnace set at 1063, but the furnace was about, inside the SACA was about 1053. And then when we had the furnace set to 1223, we were about 10 degrees less. So the plot on the left here, it does show the 4 thermocouples we have. Each one of these locations is 4 thermocouples for the individual cartridge. And what it does is this is showing us the spread of temperatures or the gradient across each cartridge. And this led us to have a delta of about a maximum of about 2.5 degrees at the 1063 hold, or a little over 4 degrees at the 1223 hold. So looking at the theoretical Sacca thermocouple error impact on the GED C5 cartridge, it was assessed at pretty much 1212 degrees Celsius. The GED Sacca thermocouple error was applied to the hot zone bore input data, and it was used in the transient GEDS thermal mass model. The thermocouple error was calculated based off each pair of equal length thermocouples, and this resulted in a variation of plus or minus 3.38 degrees Celsius. And this table here breaks down how we went about calculating the TC error. On slide 15, so this table up here, it shows the range of temperature and duration above 1205 each sample in the cartridge could have experienced, factoring in TC error. Again, the PI is interested in the duration each sample is above 1205, as well as the maximum temperature experienced. So this is kind of like that earlier table I showed, but it also includes the TC error. So if we look here at sample number 1, you can see if you factor in the TC error, the temperature ranges between right at 1201 and ranges all the way up to about 1207. So if you look at it one way, if he's only interested in the samples above 1205, it potentially never got there, or it could have been there for 63 minutes. Again, he could have been 4 to 5 degrees away during that whole time. So this is what we wanted to point out. And if you go over here to sample 7, you could have as much as almost a 20-minute difference, 15-20-minute difference in time just based off of the TC error. So it's a little change in little error in the temperature varied a lot in the time above the processing temperature. So this slide 16 here, it's just a graphical representation of what was on the previous chart, where this blue line down here is the first sample, the sample closest to the cold end, with the TC error factored in. So you can see if it was reading anomaly, this would be its curve. If it was reading on the low end, that's the curve, and if it's reading on the higher end, it's reading up here. So you can this plot shows the duration or the spread that could have happened. On slide 17, two of the key parameters for a GED science are all the Saccas processed at the same temperature for different durations. Also, analysis showing each of the samples' time temperature profiles, which will be used for energy integration. The Sacca thermocouples have a calculated error of plus or minus 3.8 degrees Celsius, where the worst measured distribution was 4.14 Celsius during processing steady state at 1223. The thermocouple error predicted temperature varied for sample 7 was between minus 10% and positive 6%, and minus 15 to positive 7% for sample 7. That gives you a little bit of a spread of how much error the TC errors could have actually changed the response. And then the TC measurement uncertainties assess whether the science goals are met isothermally in the duration of the temperature. So this error decreases using the actual TC variation compared to calculated error. So some of the lessons we learned from this experiment, from the thermal standpoint, is these short durations, such as GEDS, require transient analysis to make sure the response time of the samples is correct. And some of our future PIs we calculate their processing time in days, not minutes. So we needed to make sure we ran a transient analysis for this one. Furnace control TC drift has contributed to uncertainty in the transient response analysis. The response variation for steady state, the same heater settings is manifest as variation predicting sample transient response. Also, additional SACA cartridge outgassing mitigation techniques are required. And this goes back to the plot about the furnace pressure. As these cartridges heat up, they off gas. And so we have addressed that for future PIs with additional cartridge bake counts prior to assembling. So some forward work for GEDS. We're going to revise the analysis for each one of the GEDS runs with the associated flight data to make sure we do a better job at predicting the sample transients. And we're going to perform an analysis considering the flight TC variation. We're also going to assess if any drift was experienced by the furnace TCs over the duration of the GEDS processing, and we're going to do that by looking at the heater usage, heater power usage during each one of the cartridge runs. And then we're gonna do a full document of post-flight GEDS analysis when we get the cartridges back this December. But I found out today that might be slipping a little bit. So another thing to note on this slide, which we didn't have in previous ones, all these samples are contained in little crucibles inside of a quartz ampule. So this is one of the ampules here. So before we go on to questions, if we have the time, I was going to show, hopefully we can all see this. I was going to show recently Doug and Bob that flew up on the SpaceX mission actually did a few of our cartridge exchanges for us. And here they are swapping out one of our cartridges in the furnace on the space station. They did 2 cartridge exchanges for us and also swapped the furnace from the LGF to the SQF while they were up there. And I believe they noted that it was an easy process. I think we're gonna open up the floor to questions if anybody has any.
All right, yeah, that was really interesting. Yeah, it takes a little while before we see some questions show up in the chat. So I have a question.
Okay.
So with the SCA, do you have that planned for like different types of samples, like further down the line too, or?
So we have 4 PIs lined up right now. We are currently Dr. German, that GEDS cartridge was sintering. The next PI is Dr. Sue. He's based down in Marshall. He is doing a vapor transport analysis. Or he's essentially, it's a vapor transport. So he's growing crystals. The PI after that is Dr. Frick with Stanford. She is doing, I think it's liquid phase crystal growth. Then we have a Dr. Hoffman, out of California. He might be on at JPL, and he is doing another liquid phase sintering. So we have all the PIs have more or less different processes for what they would like.
Okay, but it's still the same basic cartridge assembly.
The cartridge is exactly the same. We can look at the slides. The cartridge is exactly the same. If we use the little laser pointer here, essentially the PI is allowed an ampule to go into this region here, and they're allowed up to 12 thermocouples, and that is about all that they can change. And we can change obviously we can change all the heater set points, and for this PI and a couple other PIs just want a real nice isothermal gradient through the hot zone. But the vapor transport PI does want a large temperature gradient to go through his hot zone and then to translate the furnace. So he wants to translate a gradient. he wants to translate a gradient through his ampule. So, but yeah, they essentially can put whatever they want up to a certain weight inside of this region towards the end of the cartridge.
Okay, and the TCs are placed on the actual SCA and not the cartridge.
They are inside the cartridge.
Oh.
So they're inside the sealed cartridge. Let's see. So that's what the cartridge looks like that is sent up there, right here. So we don't have a good image of what the thermocouples look like, but they are very small platinum type. So they're type S platinum thermocouples that run down the length of the inside of the cartridge and are just, there is a gap between the cartridge wall itself and the ampule or the sines that the thermocouple is placed at. I don't believe we have one in the backup charts. This is an actual disassembly of the GEDS cartridge, so you can see all the thermocouples up here, but they are, these alumina spacers all have notches cut in them, and so the thermocouples will actually rest in those notches.
All right, so we have a question from the chat.
Okay.
What do you suspect was off-gassing, dissolved gases, trapped gases, or some sort of reaction?
So, most of the off-gassing that we have been told is from some sort of oxides, since these, and it could just be, an oxide of it just sitting out in the lab for too long, and an oxide grows on the cartridge somewhere. These cartridges are, as I said previously, they're plasma sprayed cartridges, so the cartridges are kind of porous. So there is another, I don't want to say theory, but there's another suspicion that gas is being trapped inside the pores of the cartridges, and as you heat it up, the hotter it gets, the gas works its way out. So the two theories is that it's embedded gas in the porosity of the cartridge itself, buried inside of the molybdenum, and then the other ideas is that it's I guess it's molybdenum oxides that are coming off, or I guess dissociating. I don't know the correct term, but it's once it gets to certain temperatures, the oxygen separates off the molybdenum. At lower temperatures, it's volatiles and any liquids that are on it. There shouldn't be, but it's pretty obvious that it is. There's also oxides that are trapped in the furnace heater itself. So it's not just our cartridge that is off-gassing. It is, the furnace is actually off-gassing too. But it is mainly our cartridge.
All right, well, thanks a lot.